diagonalization. So this is engineering statistics and linear algebra. We are talking about module 5, lecture 3, part 2, eigenvalues and eigenvectors, and there we'll consider the diagonalization. In the last lecture, we just tried to talk about the introduction of the eigenvalues and eigenvectors and how we can find eigenvalues and how we can find eigenvectors is what we tried to do. And we also stated that the eigenvalues and eigenvectors are related, very thoroughly, because a eigenvalue will correspond to an eigenvector and an eigenvector will correspond to an eigenvalue. Now we will talk about the diagonalization process, and what this diagonalization is what we'll see. So diagonalization of a matrix is, so we just, the eigenvectors, generally we say that the eigenvectors will diagonalize a matrix. So the way in which we do it is, suppose we have a n by n matrix A and has n linearly independent eigenvectors. This is rather important. Linearly independent eigenvector, and if these vectors are the columns of a particular matrix S, so S is a matrix of eigenvectors which are linearly independent. Then S inverse AS is a diagonal matrix which is written by this, lambda, capital lambda. This is capital lambda. The eigenvalues of A are on the diagonal of the capital lambda. And that is written like this. S inverse AS is equal to lambda is equal to the matrix with the diagonal elements being the eigenvalues. All other values will be zeros. So the S is known as, now the S is known as the eigenvector matrix, because we are putting all the eigenvectors in the form of a matrix for the linearly independent case. And whatever we have formed here, the lambda matrix, is also known as the eigenvalue matrix. So same thing is being stated here. We are just trying to prove that. So AS is A into the S matrix over here. The S matrix is consisting of the eigenvectors. S matrix is the matrix which consists of the eigenvectors. So if you multiply this, A into X is equal to lambda into X. Same thing, we are trying to use that. So therefore, this will become lambda 1 x1, lambda 2 x2, etc. lambda n xn. So Ax is equal to lambda x is what we have written in the starting of the, eigenvalues and eigenvectors chapter. So then the trick is to split this last matrix into quite different products. Yes, lambda. So this lambda 1 x1, lambda 2 x2, lambda n xn is to be divided into two parts, x1, x2, xn, which consists of the which consists of, you need to take it on this side. So this consists of the what you call the when I what you call S. When I try to write this, then I can break it down into two parts, x1, x2, xn, lambda 1, lambda. So this again is, this is your lambda matrix, and this is your S matrix, right? This is your S matrix. So it's breaking down into S and the lambda matrix. So this consists of again the eigenvectors. So same thing we have written here. It is crucial to keep these matrices in the right order. The order of the matrix is very much important. So AS is equal to S lambda. So you multiply on both the sides by S inverse. So S inverse AS will be equal to S inverse S lambda. S inverse S will be equal to I, and hence we will have the S inverse AS is equal to lambda, or you can say A is equal to S lambda S inverse. Okay, so given A, given A, you can find the eigenvalues, then you can find the eigenvectors, then you can form the eigen, vector matrix. Then using this formula, calculate the value of the lambda, and this lambda will be always same as the diagonal elements being the eigenvalues, so that you can just check. So S is invertible because its columns, the eigenvectors, are assumed to be independent. Always we say that S is invertible because the columns are assumed to be independent. So there are a lot of remarks associated with this. If the matrix A has no repeated eigenvalues, if the matrix A has no repeated eigenvalues, the number lambda 1 to lambda n are distinct, then its n eigenvectors are automatically independent. So if we have all the eigenvalues to be not repeated, then that means they are different. Then we'll have n eigenvectors automatically independent. So any matrix with distinctive eigenvalues can be diagonalized. So if we have a matrix with different, okay, distinct or different uh, eigenvalues, then that can be easily diagonalized. So that's the condition for diagonalization. So remark 2 is diagonalizing matrix S is not unique. Generally we see that the diagonalization matrix S is not at all unique. So you can have, we can multiply the columns of S by any non-zero constant. So S can be multiplied with any non-zero constant and produce a new diagonalizing S. Okay. Then other matrix S will not produce a diagonal lambda. So you can't say that, you multiply the columns by a particular constant. Yes, you can get a different diagonal matrix, but some other type of matrices will not produce a diagonal lambda. Okay. Not all matrices possess n linearly independent vectors. So not all matrices are diagonalizable. Now it's not necessary that if they are not linearly independent, they are not diagonalizable, but if they are linearly independent, definitely they are diagonalizable. So some of the not linearly independent eigenvectors might be diagonalizable, but if they are not linearly independent, then there is a chance that they might not be diagonalizable. Okay. So the standard example of a defective matrix is mentioned over here. A is equal to 0, 0, 0, 1. So now, if you try to find A minus lambda I, then this will become minus lambda 1, 0, minus lambda. A minus lambda I will be, to find the eigenvalues, we need to write A minus lambda I and take its determinant. So that will become the determinant of minus lambda 1, 0, minus lambda. And that will give us, the determinant value will be lambda squared is equal to 0, and that will give, lambda 1 equal to lambda 2 equal to 0. Both the eigenvalues will be zeros. So if both the eigenvalues are zeros, now since it's a triangular, with zeros on the diagonal, right? We will have this like this, and hence we'll get this value. So all eigenvectors of this A are multiples of 1, 0. If we have that, then you can easily find the eigenvectors having found the eigenvalues as 1, 0. So all the eigenvectors of this A are multiples of the vector 1, 0. So 0, 1, 0, 0, x equal to 0, 0. This x can be found, and that x is nothing but C of 0. Again, this can be always done by means of, basically it is the, what you call, the process of, you can easily write over here. This is consistent because this is 0, 0, 0, and this is 0, 1, 0. So you can always write, none of them you can see that you have the, what you call, you can exchange them, might be, and then it will become 0, 0 and 0, 1. But however, you don't have, you can say that this just corresponds to a, what you call, pivot value, and this is not a pivot value. So you can write a, free variable in terms of the pivot variable, and then try to substitute the thing, and then you'll get x is equal to C of 0. So diagonalizability of A depends on enough eigenvectors. We should have enough eigenvectors. Invertibility of A depends on non-zero eigenvalues. So if you have non-zero eigenvalues, then only A is invertible. Diagonalizability of A depends on enough eigenvectors. So diagonalization can fail only if there are repeated eigenvalues. So can, here it is not must. Please remember that this is not must. Diagonalization can fail only if there are repeated eigenvalues. If there are no repeated eigenvalues, then diagonalization can definitely be done. So even then, it does not always fail. So that is why we have mentioned can. For example, A is equal to I has repeated eigenvalues 1, 1, 1, 1, 1, but it is already diagonal. So there is no shortage of eigenvectors in that case. So if eigenvectors x1 to xk correspond to different eigenvalues lambda 1 to lambda k, then those eigenvectors are linearly independent, and in such cases where they are automatically linearly independent, then diagonalization can be done. The matrix with n distinctive eigenvalues can be diagonalized, and this is a typical case. However, some of the matrices which do not have distinct eigenvalues can still be diagonalized, but there's a chance that they might not be, possible to diagonalize it also. Okay, let us take an example. If possible, diagonalize the following matrix with a similarity transformation. So A is mentioned over here with proper values over here, right? Determine whether or not A has a complete set of 3 linearly independent vectors. So you can write A minus lambda I, A minus lambda I. That means here it will become 1 minus lambda. This will become minus lambda minus lambda. This will become minus 5 minus lambda. All the other elements remaining same. Then you take the determinant of that. If you take the determinant of that, then you'll get this equation, right? So then once you take this equation, you need to find out the roots of this. The roots of this can be found out by taking the multiples of this 9. Multiples of this 9 are plus or minus 1, factors of 9 rather, factors of 9. So it is plus or minus 1, or plus or minus 3, or plus or minus 9, one of them. So if you just take that, this is more important. Check this and take the factors of this. It can be plus or minus 1, plus or minus 3, plus or minus 9. So it can be, okay. So it should be within that set. So you substitute 1 over here, this will become 1, this will become, 5, and this will become 3, and this will be 9. So 1 plus 5 plus 3 will be 9, 9 minus 9 is 0. So it satisfies that. So definitely lambda minus 1 is one of the roots. Similarly, 3 you can try to substitute, and again you will find that 3 it's possible to substitute. So, or you can just divide this equation by lambda minus 1, right? This equation can be divided by lambda minus 1. Then you will get a, quadratic value. Once you get a quadratic, equation, that can always be solved very easily by considering lambda is equal to plus or minus b, minus b plus or minus root of b square minus 4ac by 2a. Therefore, lambda equal to 1 is a simple eigenvalue, and lambda equal to minus 3 is a repeated twice. So you have, lambda equal to 1 is simple eigenvalue, lambda equal to minus 3 is repeated twice. And we say its algebraic multiplicity is 2. Algebraic multiplicity is 2. So basis for the eigenspace n of a minus 1i and n of a plus 3i are determined in the usual way. So we can find the what you call n into a minus 1i, that is span of the value over here, that will just turn out to be 1 to minus 2. N of a plus 3i will be 1 1 0 1 0 1. So we have two distinct ones over here for spanning purpose, and the multiplicity, algebraic multiplicity is 2. So therefore, geometric and algebraic multiplicity, we say that both are same. Hence, it is possible to diagonalize. And it's easy to check that when combined, these 3 eigenvalues constitute a linearly independent set. So if you substitute the different values, then you'll get 1 2 minus 2 1 1 0 1 0 1. So this will form a linearly independent set. Okay, this will constitute the linearly independent set, and that can be always checked by taking the LU decomposition of this. Okay, and then you can write this, either you can say P or you can say S. S inverse A S. Okay, in place of P we are using S, so therefore you can write S inverse A S will be 1 0 0 0 minus 3 0 0 0 minus 3. So 1 minus 3 and minus 3 are on the diagonal, indicating that 1 is multiplicity of 1 is 1, multiplicity of minus 3 is 2 roots with a minus 3 value, eigen values. Right? Okay. Now in a similar way we can try to find out for the matrix A, right? For the matrix A, the eigen values and then the eigen vectors. Okay, eigenvalues and eigenvectors, and put the eigenvectors in the form of the matrix. Yes, then find out AS and S lambda, both should be same. AS and S lambda, or you can say A is equal to, A is equal to S lambda S inverse, or you can always say lambda is equal to S inverse AS. If you multiply S inverse on both the sides, you will get lambda is equal to S inverse AS. So you can just check that, or you can just find AS is equal to S lambda, and that will give us the same value. Both the values should be same. So how do you do that? You need to find out, A is equal to, for this, A minus lambda I, A minus lambda I. Take the determinant of that. That is half minus lambda, half minus lambda. Then find the determinant of that. Once you find the determinant of that, then you will see that you have two roots, 1 and 0. Okay. With this 1 and 0, you can find the eigenvalue matrix. Roots are 1 and 0, which are there in the diagonal, and that becomes the eigenvalue matrix. Having known the eigenvalue matrix, you can try to find out the eigenvectors. The eigenvectors are this multiplied by x is equal to 0 0. A multiplied by x is equal to 0 0. So for that, we can try to find out the eigenvectors for that case, and that will give us the what you call eigenvectors put in the form of a matrix will give us this value. So eigenvectors will be 1 1 and 1 minus 1. So having found that, you can just try to test AS and S lambda, and that will be 1 0 and 1 0. So the last equation can be verified at a glance, and therefore S inverse AS is equal to lambda. Similarly, let us take another example of the rotation matrix K equal to 0 minus 1 1 0. So the determinant K minus lambda I, that means here lambda minus 1 1 lambda. So that will give us the lambda square plus 1 as the determinant of that. Lambda square plus 1 as the determinant of that. So once we find the determinant of that, then we need to find the roots of that. Roots of that will be plus I and minus I, right? Plus I and minus I, imaginary values. Imaginary values are complex values. How can a vector be rotated and still have its direction unchanged is a question which we try to ask. But however, I can be considered as changing the direction by 90 degrees, I or minus I. Clockwise or anti-clockwise. So it can't, except for the zero vector, which is useless. So we can't have a vector rotated and still have the directions unchanged, except for the zero vector, which is useless. The eigenvalues of K are imaginary numbers. Lambda 1 is equal to I and lambda 2 equal to minus I. In turning through 90 degrees, they are multiplied by I or minus I. So they become imaginary. So K minus lambda 1 I into x1. This will give us this value. And for this, we'll get the x1 solution of this will be naturally null function solution. So you need to write the, so to say, the Gauss elimination method over here and try to find out the values for x1. Similarly, you can write for K minus lambda 2 I x2, write it over here, do the Gauss elimination and find out x2 over here. So having found the value of x1, x2, you can put both of them in the form of S and then take S inverse Ks, and that turns out to be this value. Or you can try to find out the Ks and Ks and S lambda, both will turn out to be the same value, whatever it is. But however, S inverse Kx should be equal to lambda, and lambda is consisting of both, the what you call eigenvalues being in the diagonal position. So complex numbers are needed even for real matrices. There is always a possibility of complex numbers. If there are too few real eigenvalues, there are always n complex eigenvalues. Too few real eigenvalues, there are always n complex eigenvalues. Complex includes real when the imaginary part is 0. Okay. You can find the power and the product also. If the eigenvalues of A square are exactly lambda 1 square dot 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 lambda n square, and every eigenvector of A is also the eigenvector of A square. So this is very much important. Eigenvalues of A square are lambda 1 square plus lambda 2 square plus lambda. But every eigenvector of A is also the eigenvector of A squared, because of the reason that A squared AX can be written as AAX. AX can be replaced by lambda x, and that can be written as lambda AX, and that can be written as AX again can be replaced by lambda x. So lambda squared x will come out here. Thus, lambda squared is a eigenvalue of A squared with the same eigenvector x value. So the same result comes from diagonalization by squaring S inverse AS is equal to lambda. So eigenvalues of A squared is equal to, you can multiply each one of that, and you'll get lambda square, and this multiplication will just turn out to be S inverse will be equal to I. So AIA will be just AA, that is A square, and that we can write as S inverse A square, yes, that is equal to lambda square. So the matrix A square is diagonalized by the same S, so eigenvectors are unchanged. So this just gives us that the matrix A square is diagonalized by the same S, and so eigenvectors are unchanged. So eigenvalues are squared, but eigenvectors are unchanged. So this continues to hold for any power of A. So if we are asked the what you call eigenvectors, eigenvalues of A to the power k, then we need to just take the A to the lambda 1 to the power k, lambda 2 to the power k, lambda n to the power k, all the eigenvectors of A to the power k can be considered as the eigenvalues, but eigenvectors are same as the eigenvectors for A. Okay, so eigenvectors of A square are this. So we have just finished this. Okay, the eigenvectors of AK are lambda 1k dot 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 lambda nk, and each eigenvector of A is still an eigenvector of A to the power k. So when S diagonalizes A, it also diagonalizes A to the power k. So lambda to the power k is equal to S inverse AS multiplied by S inverse AS dot 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 S inverse AS, that is equal to S inverse A to the power of k S. Each S inverse cancels an S except for the first S inverse and the last S. If A is invertible, this rule also applies to its inverse. That means you can find the eigenvalues of A inverse, and that will just turn out to be 1 by lambda I, only if A is invertible. So if Ax is equal to lambda x, then x is equal to lambda A inverse x. So therefore, I can just take the lambda over here. 1 by lambda x is equal to A inverse x. So that gives us that, the A inverse is having the eigenvalue which is equal to 1 by lambda, or lambda to the power minus 1. So let us take an example. If k is a rotation of 90 degrees, then k square is rotation through 180 degrees, which means that we have ai, and k inverse is the rotation through 90 degrees. So k is given over here. K square is the square of this k into k, and k inverse is this value. So the eigenvalues of k are I and minus I, their squares are -1 and -1. This reciprocals are 1 by I is equal to minus I, 1 by minus I is equal to I. Then K4 is a complete rotation through 360 degrees. So K is 190% degrees rotated. K to the power 4 is a complete rotation through 360 degrees. So K to the power 4 is 1001. And also, lambda to the power 4 is I to the power 4 0 0 minus I to the power 4. That will be 1001. So diagonalizable matrices share the same eigen matrix S if and only if AB is equal to BA. Okay, diagonalizable matrices share the same eigenvector S if and only if AB is equal to BA. So whenever we have two different matrices A and B, then if AB is equal to BA, then the diagonalizable matrices share the same eigenvector matrix. So for this we can prove this. Okay, if the same S diagonalizes both A and the what you call B, A can be written like this and B can be written like this. We can multiply in either order. That means AB you can write like this. Okay, we can write VA like this. Now these are values lambda 2, lambda 1 are just two different matrices with diagonal elements. You can easily commute them. Lambda 1, lambda 2 is equal to lambda 2, lambda 1, and that will give us the diagonal matrix. It's possible to commute, and we have AB is equal to BA. AB is equal to BA. So both are same. If they can commute, then AB is equal to BA. So in the opposite direction, suppose AB is equal to BA, starting from AX equal to lambda X, we have ABX is equal to BAX is equal to B lambda X is equal to lambda BX. Thus, X and BX are both eigenvectors of A and what you call sharing the same lambda, or else Bx is equal to 0. So lambda will be same. That means the eigenvalues will be same for A and B if you have the property of AB is equal to B. Okay, there are some of the examples given over here in these two slides. Okay, you can stop the video at that time when it is recorded and kept, and you can just try to solve these numericals. Okay. We'll stop at this video. If you have any questions, we'll take what you call